it's time now to start talking about the idea of line integrals. Now here's the basic idea behind line integral. We first introduced the idea of a dot product by using it to calculate the amount of work done when we're moving an object in a straight line over a specified distance by applying a constant force. Now what if this object moves along a curved line? What if the force applied is variable, it's not constant? Line integrals allow us to address these types. Oops, this is supposed to be these. Got the S in there. These types of problems, which leads to many different applications. First, I want to start off with the idea of looking specifically at parameterized curves. Now, consider a surface in 3 space and a curve in the xy plane. If we extend that curve from the xy plane up to the surface, we create a curved wall sort of a thing. Is most likely it has variable height. So let's see if I can just quickly draw a picture of what I'm talking about here. So I'm dealing with 3 space. And let's just say I have some surface setting here in 3 space. And actually, I don't want that thickness there. I'm just interested in the surface itself. And then I have this parameterized curve down here on the xy plane. So if I extend this up to the surface, what I'm going to get is basically a wall where this right here, this line right here, is where, I should have picked a different color, sorry I kind of missed, is where this curve, the extension of it, intersects this surface. So if we get rid of the surface, we've got this thing that kind of looks like this. Now it's shaped the way we see it on the xy plane, but the height could be variable because of whatever this surface is. We don't know the actual shape of this surface. So I can think of this basically as being like a wall or a curtain. Now the line integral gives us a means of actually calculating the area of one side of this wall, which has many interpretations in physics. Now let's let C be a smooth plane curve, where this right here, what I wrote earlier, that's C right there, on the xy plane, represented by the parameterization x equals x of t, y equals y of t, and t goes from a to b. Or equivalently by the vector equation r of t equals x of ti plus y of tj. So looking down now on the xy plane, I have this parameterized curve from a to b. And this is a to b. I shouldn't write it like that. This is t goes from a to b. Now if I divide C into subarcs, now each arc is going to have a length. Each subarc is going to have a length of, let's call it delta SI. And I'm going to let the arbitrary point PI, XI, YI, stars, be any point on C in the ith interval of f of xy, where f of xy, I should probably write this, any point on the ith interval and we're going to let f of xy, we're going to think this is a projection of the curve C onto the surface. And I'm going to denote the surface as capital F of xy. Now with this notation, I'm now thinking f of xy, or actually I should write that xi, yi star, because this x and y is the arbitrary point in the ith interval of c. This is still c. So this is actually the distance from C to the surface. Of course, at this point, xi, yi. Now, because of this, we can say that f of xi, yi, again, this is the arbitrary point on the ith interval, times delta si is now going to approximate the area of the ith subinterval. So if I go back to this diagram I did earlier here, so I have some arbitrary point, say right here, whoops, I'm having problems with my colors. There we go. So this is some arbitrary point xi star, yi star. Now f of xi, yi is going to be up here. So this is the height. And then the arc length down here is going to be approximately, or is going to be listed as, or notated as delta si. So if I take this height and I multiply it by this arc length, it's a good approximation for the total area for this. This point should be over here the way I drew it. Sorry about that. We're going to move it real quickly. There we go. So that should be approximately the area of this particular ith interval. So with that, I can say the total area is going to be approximately the sum I equals 1 to n of f of xi, yi times delta si. So of course, you know, the next thing we're going to do, we're going to end up taking the limit. So if I take the limit as n goes to infinity of the sum I equals 1 to n of f of xi, yi times delta si. And also, by the way, these delta si's are constant. All these subintervals are going to be of equal length. Otherwise, I have to take a look at the norm of the partition going to 0. I need to bring in that idea. This is going to give me the, this will give me the definition for the line integral of little f along C. So this is going to end up being the integral over the curve of f of xy. That's my little f. This is the, think of this as the projection of this curve onto the surface. ds. Of course, if the limit exists. Now I recall from like back in, I think Calc 1, it might have been Calc 2, I don't recall off the top of my head. The arc length of a parameterized plane curve is given by s equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Again, this is arc length of a parameterized curve. So what this does is this implies then that ds, to take the derivative of both sides, is simply going to be equal to the square root of all of this. So actually, I'm sorry, ds dt equals the square root of all that. That would then imply that ds equals the square root of dx dt squared plus dy dt squared dt. Now, the important reason that we did this is this now gives me a way to actually integrate this. This is a nice definition, but it didn't really tell us or give us a way to actually evaluate the thing. Well, this does. So that gives me then is that my line integral then becomes the integral. Well, let's write this whole thing out. Over the curve, the line integral f of x, y, ds is now equal to integral from a to b, because the a to b would obviously reflect the domain of t, of f of x, y times the square root of dx dt squared plus dy dt squared dt, which I could also write in a slightly more compact form. To remember, r of t is how we parameterize a curve. So r prime of t is going to be dx dt dy dt, and then obviously the magnitude is just this thing. Now, it's important to note that there's many different possible parameterizations of any curve on the xy plane. The value of the line integral does not depend on the parameterization, provided the curve is actually traversed only once. So if this is a curve that I'm looking for on the xy plane, say from this point to this point, there's more than one parameterization I can find for this. There's more than one parametric function to describe it. But as long as a or t goes from a to b, as long as I only cross this curve, not cross it, but pass through this curve, go along this curve, travel the path of the curve, that's what I'm trying to say, once, then the parameterization that's chosen is irrelevant because the distance you're traveling is actually the same. Now, one last quick thought here. If we have the special case where C is a line segment from A0 to B0, then what we can do is we can parameterize this as simply x equals x and y equals 0. So this line integral over the curve of f of x, y ds becomes the integral from a to b of f of x 0 times the square root of dx dt squared plus 0 squared dt, which is obviously just the integral from a to b of f of x dx. So you take the square root of this, the dt is going to cancel, and this is going to be simply dx. So that works out very nicely. So in other words, this simply reduces to the ordinary integral of a single variable function when I'm dealing with a line segment like this.